everyone for joining. I know it's a Wednesday, middle of the week, afternoon, and clearly, as you saw in my chat, I need a little bit more coffee. But I'm excited to talk about all the things that we're doing here at Neural Magic. As Sasha pointed out, I lead our product efforts here, and it's a lot of time spent working and talking to developers as well as folks who are looking to improve business outcomes with deep learning. And you're going to kind of get a distilled version of who we are, what we do, what we're trying to go after. And then I'll be passing it over to my colleague Michael, who's going to actually show you live, right, some of our code running, and you're going to get a feel for the experience you're going to get with Neural Magic, and also some of the value props that we're going to be talking about soon. So with that, why don't we go to the next slide? And I hope we can keep this somewhat interactive. I know it's a little bit difficult in web format, but please, ask questions, ping us. Michael and I are here to, answer questions on behalf of, the material that we're presenting. And I thought I would start off the conversation by, talking about some of the common problems we see people having. And it's very easy to jump in and assume that Neural Magic is purely a performance company, and that's all we do. And based on some of the things that you probably have read about us, GPU class performance, it's not hard to understand why, right? But when we actually talk to users and developers, whether they're machine learning engineers, DevOps engineers, application engineers, we kind of see this intricate balance that they're trying to maintain, right? On the machine learning side, we're constantly presented with, what model should I be running? This is the sort of data I'm capturing. These are my training pipelines. I need to make sure it works with this deployment pipeline. Things like performance matter to me. Things like accuracy matter to my business constituents. And oh, by the way, I'm trying to figure out also how to incorporate state-of-the-art research that's coming out weekly, monthly, yearly. And while they're doing that, they also have this balancing act of trying to make sure that the machine learning efforts that they're underway on also align to the trends that we're seeing in the industry around software best practices, right? With the advent of SaaS platforms, consumption-based pricing, we see a explosion of adoption in things like Kubernetes and Docker and all of the different OS choices that you have, and being able to integrate this directly into the CI/CD pipelines people are using and familiar with, and then sort of managing the life cycle around all of this. And somehow, if you have a team that's been able to tackle and get a good grasp of all of the machine learning intricacies, then sort of figure out how to balance that with some of the best software best practices out there, now your runtime or your outcomes also then become dependent on the infrastructure you're running on, right? What hardware do I have available? Am I running this on bare metal because I need to be running this closer to where my data is generated? Am I running this in a public cloud? Am I running this in a private cloud on-prem, right? All of this matters, and all of this becomes tied together. So what we want to do at Neural Magic is to try to simplify what you're seeing here, right? And make the end-to-end running and deployment of deep learning applications more possible, right? And do this with ease, and try to simplify some of the decisions and balancing that a lot of the developers that we're talking to have to face. So if you go to the next slide, what do we actually do, right? So to address this, we fundamentally, at its core, have built a software accelerator. But that software accelerator has been designed to run on ubiquitous, available, accessible commodity hardware, in this case, CPUs, right? So we've designed a runtime and compilation engine that's going to get you GPU level or GPU class performance, right, on commodity CPUs. And while performance is one vector of a value proposition, because we are a software offering, what that allows us to do is seamlessly integrate into all of those software standard best practices I mentioned earlier, right? We fit natively into Kubernetes and Docker managed deployments. we are thinking cloud first. We are thinking different levels of isolation. If people want to run in user space, we give them that option to pip install our software and run. And then I think what's unique about our offerings and sort of the premise of what we do is, in addition to creating performance in order to get achievable outcomes with accuracy, in addition to adopting standard best practices, in addition to simplifying the choice around hardware by making it run on something that almost everybody has already, we also unlock a unique ability within the ML space to actually run larger models with larger inputs, because we can take better advantage of that hardware infrastructure that we're running on that happens to have larger cache sizes. So we'll talk a little bit about how we do that as we go on. So you're hearing a little bit about what we do, sort of the fundamentals of what we are as a company. Now, what do we offer our end users? And today, as Sasha mentioned, everything that you see here today is available in GitHub, as well as to download in PyPy, with your standard pip install. And you'll see some of this as part of the demo and some of this in our material later on. But you can kind of think of our offerings broken into two simplistic categories. There's the runtime in the engine. So, the ability to actually generate and execute, graphs and neural networks at GPU speeds on commodity CPUs. And that is actually on the right-hand side of this chart, our Deep Sparse Engine. And today, we invoke this engine, with Python, with C++ APIs, and it's designed to run and take advantage of very specific vector instruction sets that are on our CPUs. And that's how we're able to generate and optimize for performance. And that's sort of one aspect, right? Which is the execution side of it. Now, in addition to being able to execute neural networks, one of the things we do at execution or at process time is run sparse neural networks really well. And what sparse neural networks are is effectively us taking advantage of the sparsity in nodes within a network and using a unstructured pruning technique, in addition to some other, I would say, methods, which you'll hear Michael talk about, compress these networks while maintaining speed, and also giving our users the flexibility and the type of accuracy recovery they want to have. And the three boxes on the left here really represent different ways to create these sparse deep learning networks that will then run performantly in our engine. The SparseZoo on the left-hand side is our way of tackling the pre-trained model problem. So if you are unsure of what domain, if you're unsure of what model to choose from, or if you just want time to value, we give you pre-trained deep learning models by domain with data sets that are effectively ready to download, load, and go, right, in terms of running on our engine for performance as well as accuracy recovery. And in fact, this is what Michael is going to demonstrate and show you a little bit later. But we also know that many of the machine learning engineers and data scientists out there want the ability to customize, especially when it comes to tailoring to training pipelines and deployment pipelines. So that's where we introduce SparseML. SparseML is our way of customizing the process by which you create these sparse networks in your library of choice. So, as an example, PyTorch, TensorFlow, Keras, depending on the deep learning framework you're running in, we have those libraries and the associated code to customize and tailor to your specific pipelines. And then Sparsify is the last one on here. And it's meant to almost be a hybrid between the SparseZoo and SparseML in the fact that it's taken the complexity of pruning and creating sparse networks out by automating some of that process. So you load a model, you load a data set, and Sparsify is creating and producing a recipe for you to follow based on your network, based on the weights that it's and inputs that you're giving it to generate a sparse network that will run performantly in the engine. So if we go to the next slide, what we wanted to show you here is where are some of the domains and what are some of the applicable use cases you can tackle with neural magic. And at the highest level, the two main market domains we are focused on are computer vision and natural language processing, which you'll see in this deck. The first one here is computer vision. So the types of use cases we support today are image classification, object detection, and we're very recently, in our next release, in fact, in the next 2 weeks, we'll have a model, pre-trained model, sparse pre-trained model that will be supporting image segmentation. So the kinds of models that you would expect to see in our SparseZoo are probably ones you'd be familiar with if you're already in and investigating and prototyping in the vision space. The ResNets, the mobile nets, the VGGs, the YOLOs, and most recently will be YOLACT. And what I failed to mention on the prior slide, which you'll see when Michael demos, is we don't just offer pre-trained models, but if you step back, I mentioned that the software and the offerings that we deliver really represent two key themes. How do I reduce the amount of compute? And then how do I sort of accelerate memory-bound processes, right? So those three boxes, the Sparsify, pre-trained models, and SparseML, are focused on how do you reduce the amount of compute. And the compiler or engine or our runtime is all about executing that network, right, on commodity hardware. We want to offer different flavors of models in our zoo so that people can pick and choose the SLA that matters most. And this is not just, I would say, performance related. This could be compression related, right? So we'll offer full precision models. We'll offer full precision sparse models. We'll offer quantized models, and we'll also offer what we call sparse quantized, which is our lower bit precision integer 8 models. So these are the kinds of models and variety you would expect to see when you enter our SparseZoo with the models you see on this page. And the use cases are fairly typical that you would expect, right? Quality assurance on a manufacturing floor, visual search for retail, video processing right at the edge, maybe 5G. And even in certain cases in medical, we've had and encountered use cases around microscopy, right? So how can we get fine-grained segmentation resolution on a high-resolution image for medical purposes? So we just wanted to give you a little bit of a flavor of the tasks that you would be able to accomplish. And then on the NLP side, which I would say is the second primary domain that we're going after, today we're focused on BERT. And what you'll see in the future from us are more transformer-based architectures. In the future, we envision models like T5, GPT-2, and others. And the reason why we've focused on these transformer models is because these are typically over-parameterized. So you have lots and lots of parameters that we feel lend itself nicely to the compression techniques that we offer in our ML tooling. And then those, once we've pruned and sparsified and created compressed sparse representations, run for speed and accuracy, right, in our engine or runtime. And today, the types of data sets that we support are Q&A, so that's our foremost, so Squad if you're familiar. And then book corpus and Wikitext is something that we just released. And the reason why I mentioned these two specifically is we actually have pre-trained models in our zoo that are directly correlated to these data sets, right? So these are literally load and go for Q&A and different types of NLP use cases, such as segment classification, entity recognition, sentiment analysis, right? So a very common NLP associated task that you would see with BERT. If I go to the next slide, we're giving you a little bit of a flavor of what performance looks like. So, when Michael shows you the SparseZoo, you'll see there's a couple of different models to choose from, as I mentioned before. We've given our users almost a la carte menu of performance, accuracy, and compression, and the user can decide what SLA matters most to them. So what you see on this graph, aside from sort of our continued investment in performance as one of our key value propositions, which you can see from the different releases, is we've offered different lower bit precision models with different sparsities, right? Because all of these will correlate to different recovered models in terms of accuracy. And you can kind of see how the different sparsity percentages correlate to performance. And then you'll see in our SparseZoo when Michael demos what the correlating recoverability looks like. And we also gave a compare to Microsoft Onyx runtime. So for most people who are running BERT on CPUs today, Onyx and Microsoft have spent a lot of time optimizing their engine and runtime, right, to run these models performantly. So you can get a little bit of a sense of, how Neural Magic's performance compares. And all of the benchmarking that we typically do and produce and show externally, especially on our website, are run on standard compute optimized instances on AWS. So in this case, it happens to be a 24-core Intel AWS system, C5 12x large, that takes advantage of the vector instruction sets that we support today in our engine. And for BERT, this happens to be a sequence length of 128 and batch size 32. But you'll see a little bit more in terms of the demo that Michael is going to take you through. And then last, before we jump into the demo, we wanted to give you a sense of what the developer experience looks and feels like. So you'll see the look and the feel from Michael when he goes through the demo. But at a macro level, what the ideal sort of flow looks like is download and install in user space, right? You're not forced to run this in a SaaS cloud. You're not forced to run this where you don't want to. Data privacy is completely up to you and sort of by the regulations that you have in place. So, go to our GitHub, go to PyPy, and it's as simple as pip install Deep Sparse, right, to download our software today. And then once you're in, you'll see we have a flow for getting started. We want it to be simple for people to find the models that are relevant to them for the tasks that we mentioned before, along with the data sets, and then also to easily navigate what SLA they care most about, and then benchmark and try them. So you'll see in our SparseZoo, the layout of the model and the flow, but then more importantly, in addition to the assets to just download and benchmark, we want our users to know that you have the ability to then take the next step of running with your data, right? So we know that even if you start with a pre-trained model, Squad may be interesting, ImageNet may be interesting, and you'll get a sense of what performance looks like by just a simple benchmarking task. But the next step typically then involves running it with your own private data set. So we offer both tutorials and recipes that take advantage of known industry techniques like transfer learning, right, as a simple example. And what we've added on top of that is we've simplified sparse transfer learning, right, which is transfer learning from one of our sparse or pre-trained networks. And all of this is designed to get you from prototyping to deployment, right, with your data set faster. So with that, why don't I pause and turn it over to Michael to let him introduce himself and also walk you through some of what I just showed you.
Yeah, thank you, Gaurav, for the handoff, and thank you, Sasha, for running the slides. I guess I can take it from here. But yeah, just to introduce myself, my name is Michael. I'll be taking you through our demo today. I am one of the lead engineering managers on the runtime team, so I can obviously adequately handle any questions you have about the engine. As for ML things, I will do my best, but we have some really smart ML scientists here, so it might be a little bit difficult to cover everything. But yeah, so we can start off. I'd like to take you through a demo of what we've done latest on BERT question answering. And so just starting from Neural Magic, we can go to the SparseZoo. We have a special get started section where we can dig into what we have available for BERT. So for first, I'd like to talk about where we started from the machine learning side. Where we started from, and you can find this all in our Neural Magic SparseML public GitHub. This is in our Hugging Face transformers integrations. We took, Hugging Face's excellent transformers library, essentially the standard reference implementation of BERT. Then we augmented it to support different types of sparsification. We like to call it compound sparsification, so including easy ways to support knowledge distillation, unstructured parameter pruning, quantization, as well as layer dropping. So it allows us to sort of pick and choose from state-of-the-art work that's already been published, such as prune BERT for unstructured pruning, or distill BERT for layer dropping, or mobile BERT for knowledge distillation. And we tried to do our best to show you what we did for the Squad data set and soon to be other data sets in the public, so you can see reproducible recipes that we used to apply all these sparsification techniques on the BERT models, and our weights and biases projects are open, so you can see, you know, how the accuracy metrics progressed as we started pruning and loss and things like this. Happy to dig in later if people are interested. But to start with, I think we can go back to the models that we actually produced for you today on Squad. We have more models for other data sets, but we're just going to focus on Squad today. And so if you notice, there's a lot of different types of models. The important thing to note is that this base none model is your usual dense FP32 pre-trained BERT-based 12-layer you would get from Hugging Face. And we report on different metrics on this. So the exact match accuracy on the Squad data set, speed, this is items per second. We measured this, I believe, batch size 32 on a C5 12x large, which is what I'll be showing you this demo on today, and sort of the size of the model once exported for inference. And here we have a large swath of different models we've produced. I'll try to talk through the major things. So pruned means obviously this is unstructured pruned. You know, some weights are set to zeros, and this is at various degrees that we play with at levels of sparsity in order to maintain accuracy. We also denote when if it's 6 layers or 3 layers. If it's not listed here, it's a 12-layer base model with no layers dropped. And we also have a quant to represent if it's sparse quantization. This is another compound technique that allows us to get more speed while maintaining accuracy and decreasing size. We also report if the model is conservative, this means it very closely matches or exceeds the original quality of the dense FP32 base. We use moderate to say it's within 99% of accuracy, and then aggressive with the number after it denotes, you know, the percentage. So this model is 84% recovered accuracy compared to the base. This one is 98%. So what I'd like to focus on today is benchmarking, which we'll go through. I'd also like to take a look at comparing the dense model base with, let's see, this prune quant 6-layer at 96% of the original accuracy, because this is essentially an order of magnitude faster in items per second, or I guess throughput items per second, let's say, and an order of magnitude smaller in size, which I think is pretty impressive. I'd like to take you through it. Okay, so on the right here, I have a setup on an AWS C5 12x large instance. That doesn't mean anything to you. Just know it has 24 cores and it has a modern Intel chipset. But so first of all, looking into our benchmarking example, this is all in our DeepSparse repository, also public open source DeepSparse examples, Hugging Face transformers. So first thing we can do is make sure that we pull the repository down, or actually first, let me make sure we're in a virtual environment to keep things clean. My Python users out there. So we can clone the repository, navigate to the folder we just mentioned, Hugging Face. Yep. Now we can pip install the requirements in order to run these demos. And this will take just a sec. And so we have our benchmarking example. Sorry, I'll make it a bit larger. So we have a benchmarking script that by default uses all the cores on the system. And we can just give it a SparseZoo model ID. So we can just do Python benchmark.python, and we can go back to, this is our dense model with the original accuracy. We can copy the ID from there, paste it in here, and start downloading it from the SparseZoo. Yeah, it's a pretty large model, the original BERT. So be patient.
And Michael,
with
maybe while that's running, there was a question in the chat about the cores as you're demoing here. 24 physical cores 12 hyper-threaded?
Yeah, so it's 24 physical cores and 48 threads, hyperthreads. If we, yeah, I believe. Yeah, 24 cores. So this dense model is running. It's going to be a bit slow. I'm sorry, but you have to wait. I guess it kind of proves a point that this isn't as usable of a model. So we're running through all of our iterations one at a time. You can see, yeah, this is running batch size 32 on 24 cores. Running in the DeepSparse Engine.
There was another question maybe that you could help jump in on here too.
Yeah, more examples for classification data set. Yeah, absolutely. We're working on text classification, document summarization. Remind me if I'm missing, Gaurav.
I know we have text sequence classification. I know there's more in the entity recognition and extraction that we're looking at doing as well. And then of course, we'd love to hear, some of the use cases I think that people here might be running and what we could do to support that in the future.
Yeah, absolutely.
And I thought Ben had an interesting question here too about pruned model accuracy and how would a pruned model accuracy exceed the base model accuracy? Does pruning sometimes help with overfitting?
Yeah, so pruning can definitely help with with like better generalization on the downstream task. As we know, these like modern models can have tons of parameters and can sometimes over parameterize on their training set. In this case, actually, this is kind of a known feature of BERT that the base model that has been pre-trained and released is a little bit undertrained. I believe this is the Roberta paper that showed this. If you keep training it, you can actually pump the accuracy a little bit. I believe our base model is taking the Hugging Face base, so you might be able to get a little bit more accuracy just by doing some additional training. You can check that on our weights and biases project to double check us. But so we ran this benchmark on the dense model. Let me go ahead and kick off this 6-layer prune quantized. And hopefully this will be a lot faster, less data to download, and faster iterations. So you'll see in this this dense benchmark, we already have some metrics. We show you, so this is batch size 32, we show you milliseconds per batch and items per second, so 65, pretty good. So on this prune quantized model, you can see it's a big improvement. So in order of magnitude more items per second, we're looking at 670. This is for the model with 96% of the base accuracy, base exact match. And so with these benchmarks shown that we can kind of verify the performance on this model, we can go ahead and look at an example application to show that these models are actually real and we're not just showing jumbled up numbers. So let me open a notebook to make this a little bit easier for y'all to keep up with what I'm doing here. This will open up. Yeah, nice. Okay, so we can make just an empty notebook. Let's see, I have a little example paste. So we made this pipelines library, which is very similar to Hugging Face's own pipelines that they export in transformers. This essentially makes it so you can take an Onyx file or a non-Onyx file for a BERT or a transformer model, or like a sparse model stub, SparseZoo model stub. And like transformers, you can give it the task you would like this pipeline to do and the model, and it will essentially set up this callable object with pre-processing, post-processing, and then the engine running, the model running in the DeepSparse engine optimized so that you can just give this pipeline straight text like you would for your task. So here we can do something like where do I work? We can give it some information about myself. So like my name is Michael and I work in Somerville. And then we can run this and sort of see the result. Oh, here I have the prune quant model. Okay, so it gives us a score of how confident it is about its answer, how good I think it did. So 93%. It's pretty confident, and its answer is Somerville, which is correct. We can also give this a run through with the dense model with all the full accuracy. We can hopefully see it'll give a similar answer. And yeah, this one's a little bit more confident with its score, but it's still up there, 96%, and same answer, Somerville. We can maybe poke it a bit, say like, what's my name? It's really sure about this, 99%. My name is Michael. So yeah, that's an example of an application for it. We also have, an example deployment. So if you would want to set this up like on AWS or some sort of hosted solution, we make it easy, at least as an example, to set up, an HTTP endpoint with a server on the back end running with the engine, so that you can have like basically a pipeline client that can just send these same queries to the server, and you can just get responses off a remote server for whatever your edge application is. Yeah, pretty cool. I'll take a look at the questions.
Yeah, maybe that's a good one with the performance. How does it scale, batch size, cores, and instances,
Yeah. So we can go ahead and run this ourselves. Actually, just to point out, we do have on the website. Sorry, here's my cat. Her name's B. She wants to be involved. Okay, we actually don't have this anymore. But so you can do all these things in the benchmark application. So I'm pretty sure someone asked, how does it scale across cores? And so if we go look at this benchmark application, we can see it has a num_cores argument. We can go ahead. So by default, you can see up here it was running with 24 cores. We can run this down to say 10 cores. And so let's remember, maybe I should have done 12 to make it perfect half. But so with 24 cores, we were 670. And with 10 cores, we were 447. So 670 divided by 474. Did that reverse. 70%. So actually, scaling with cores is linear up to a certain point, and then you start to drop off once you can essentially satisfy the amount of memory that your like whole system can produce. And so this is the whole point actually of pruning and quantizing and layer dropping all these compound sparsification. It's sort of reduce the compute of your model and make the model more memory bound essentially. And something that we're working on within the engine, within our own IP, is these sort of tensor columns, this depth-wise execution we talk about on our technology page, which allows us to sort of make the model keep more of the model's computations in cache, so we don't actually have to go to memory between layers, and we can stream data between layers, keeping all of the activations within cache. And on a graph that Gaurav showed of essentially how we were improving every release, this is something that we're continuing to work on and enabling more depth-wise execution in transformers, and really excited to eventually show more transformers for y'all, but it requires a lot of work to package it up and make these nice pipelines, make it a usable thing So it's not just a benchmark we're showing. We want to make sure it's something that you can take and replicate, something that you can take and use, build applications with. That's what we really want to see here. But yeah.
And I'll reiterate one of the questions I think that was asked earlier, is all of our tooling and code open source? So if you remember back to the more generic product slide, we had sort of 4 boxes, and the 3 boxes on the left were SparseZoo, SparseML, and Sparsify. All of those today are open source. And then the last one was the Deep Sparse Engine. That's free, but still closed today. So that, as Michael was saying, there's a lot of proprietary techniques that we're putting into this engine to achieve some of this speed up. So it is freely, free to download, free to use, but it is closed source.
Yeah, and to just add, like with all the SparseML and all the optimization techniques that we've transferred from research to something that engineers can actually use, these are optimizations that just make the model better wherever you want to deploy it. Decreasing model size, decreasing the number of parameters, quantizing data types from FP32 to int8. These are things that just make your model objectively better and more efficient on wherever you decide to run it. It's just with the engine, we know how to make things run well on CPUs.
Yeah, and that's a good point, because we have users come in, and right now I'm kind of answering hopefully questions, because we get a lot of these are sometimes common, but as Michael said, the engine, when we look at operator support and sort of building operator support, there are things that we know that will run extremely well in the engine, that we generalize to architectures, which then become models that we support, which we then make pre-trained models for, so that all of that, that happy path continues to work well. But that doesn't mean that your only entry point in using neural magic in our software is our pre-trained models. We do that from a simplicity and a time to value standpoint, so that people can load and go, test it, run it with their data, transfer, learn, and then deploy, and make it as simple as that. But as we mentioned earlier, if you're more into custom pipelines, especially training pipelines, you can run private models. And we would want to work with you ideally to make sure that the architecture that you're running is similar enough to one of the pre-trained models that we have. But that's where SparseML and some of our other tooling comes into play, where you can effectively create recipes to then prune, your own dense models, or potentially prune, your own sparse models, and get them in a state to run in our engine. So you kind of have a dual entry point to work with neural magic here.
Yeah.
I'm trying to think of other questions.
Yeah. Any more questions from y'all?
And there's, if you are interested in, learning more, and I think there's another slide, which, kind of next steps here. But we'd love to continue to talk and, reach out to us to further discuss any of this with you. Use cases, how we're packaging, sort of roadmap, timelines, etc. So I think maybe this one goes back to Sasha now for the last slide. There aren't any others.
Oh, yeah, let me pass it back.
Oh, we had one more question from Dale. Batch size impact. So how does like batch size 1 compare to 64, 256, Michael? And maybe some of this might be model dependent, but
yeah, definitely model dependent. For batch size 1, there's also, are you talking about throughput for batch size 1, or are you interested for like latency? This is an interesting trade-off, especially if you do multi-streaming. But yeah, generally for batch size 1, you're going to see a decrease. I think it's hard to make generalizations, but if we're talking like scales of speed up, if we can expect like a 4x speed up at a large batch size, we can maybe expect like a 2x speed up for batch size 1. This always like depends on like what's the size of your images that you're feeding, or your sequence length that you're feeding in. It's all the batch size really gives us is enough compute to make the model compute bound, which then makes these techniques that reduce compute make the memory more memory bound, more effective. So it's kind of a multivariate problem, but yeah, everything we showed you today is free and you can absolutely recreate it. The only thing I had to pay for was the AWS machine. So feel free to like run your own experiments and talk to us in our Slack or discourse forums, and we'd be happy to hear from you. Oh, I now see from Dale, he wanted latency. So we have a blog on this. Sasha, do you know where the blog is? I can't find it anymore.
Yes, neuralmagic.com/blog.
There we go.
And while we're looking for that, I know Matthew just asked a question on, what we've demoed is free. Do we charge? We do charge. So what you're seeing right now is sort of I would say, pre-deployment, exploration, as we expect people to run and execute and, push this into production or push this into a commercial application. There are certain, I would say, features that we are envisioning people will want. Whether it's backporting, services, support, and there are ways that we start to charge around some of that as well as consumption from a compute standpoint. So, and we will be talking a little bit more in Q1 timeframe about a more definitive commercial offering. And then I see there's another question. Would there be more pipelines like the question and answering one shown? I'm assuming you mean training pipelines, like outside of just Hugging Face? And that's, we would definitely be, interested in learning a little bit more on, what pipelines people would be interested in. And what we've also noticed is, kind of piggybacking on the prior question, the fact that we're open source for a majority of what we offer today, we've actually seen the community and members starting to build integrations. In fact, very recently we had a PyTorch Lightning integration that was completely community driven in terms of integration with our SparseML libraries.
Yeah. Still working on your batch size 1 results, Dale. Just running the benchmark on the machine for batch size 1. I can say like on here for the prune quantized 6-layer model, I get like 5 milliseconds per batch, or like about 200 images per second for batch size 1, and 30 milliseconds per batch for the dense FP32, or 33 images per second. So a pretty good ratio there. Still almost an order of magnitude getting there.
And, like just to piggyback on that too, just what we talked about earlier in some of those first slides is we want to make this more usable. And, Michael mentioned compound sparsity and sparsification, right? We offer, at least with BERT today, 3 different flavors of models, like a 12-layer, which, is comparable to your BERT based uncased, a 6-layer, which is very close to distilled BERT. And then we even offer this 3-layer, right? So, I'm sure latency and throughput's going to vary depending on which one you use because you've optimized for either performance or recoverability, but you get, nuances and choice, right, based on the applications that you're running with us. Okay, with that, Sasha, I guess we turn it back to you.
Oh, I think there's one more question from Dale. Do I see that right?
Do you work before, after, or around OpenVINO? You could say around. So think of them as also as a compiler and an engine. And I think this is where, that first slide I think is very important because I'd like to think of us as just much more than a compiler, right? What we're able to offer, I think, is a little bit different in terms of sort of the end-to-end, especially as we target more on the application side. And there was a question that I answered, I think, in the chat, which was, what could we do from an availability standpoint and how can we simplify, could we see ourselves in marketplaces? And the answer is yes. You're seeing sort of some of the current instantiation of our products and offerings, and we are envisioning new types of offerings that even simplify what Michael is showing you, right? Like as an example, like a containerized deployment where a lot of the abstraction in terms of modeling and decision-making around models gets abstracted. You know, for an end user who comes to Neural Magic and just says, I have a sentiment analysis app and I'd love to just run that on a CPU, right? Close to where my conversational AI agent is, as an example. Like, I don't care what the model is. I just need sub, 1 or 2 millisecond latency, right? And like, we envision that kind of product in the future as well.
So I think Dale wants us to answer pretty directly. Do you need?
Oh no, we don't need OpenVINO.
We don't use OpenVINO at all. We are. You could call us a competitor to OpenVINO.
All right. Thank you so much. Thank you, Gaurav, and thank you, Michael, and especially thank you for everybody that joined and for asking questions. This doesn't have to stop right now by any means. We are here for our community at all times. So I just have one more slide at the end. Can you guys see my conclusion slide? Yeah, I think so. So thank you for listening. If you're all the info, everything you saw today, you can pretty much access from our website. So feel free to visit neuralmagic.com. SparseZoo is linked from there, all of our documentations, ways to contact us. I still encourage you one more time, please, to join our Slack and Discourse forums by going to neuralmagic.com/community. Any questions you have, you can definitely get answers there. And if you run into any issues, and we're always looking for feedback, so feedback is much more than appreciated. Once again, thank you, and we hope to see you again soon.